choosing the right data structures for your project in the world of software development and algorithm design. Selecting the appropriate data structure is crucial for building efficient and scalable applications. The right choice can dramatically impact performance, memory usage, and code maintainability. Whether you're working on algorithms for competitive coding, optimizing database queries, or designing complex systems, understanding various data structures empowers you to make informed decisions that align with your project's requirements. The foundation of efficient programming data structures form the backbone of any program by organizing data in ways that allow efficient access and modification. They enable programmers to manage large volumes of information effectively while maintaining optimal runtime complexity. Selecting an inappropriate data structure often leads to inefficiencies such as excessive time spent searching through elements or unnecessary memory consumption due to poor organization techniques. Common types include arrays, linked lists, stacks, queues, trees, graphs, and hash tables, each serving distinct purposes based on their internal implementation characteristics. Arrays provide fast random access but have fixed size limitations which may require frequent reallocation during dynamic operations. Linked lists allow flexible insertion/deletion at arbitrary positions, though they sacrifice direct element accessibility compared to arrays. Evaluating time complexity trade-offs. Understanding how different data structures handle insertions, deletions, lookups, and traversals helps determine which one best fits your use case scenarios. For instance, when implementing undo functionality where last actions need quick retrieval without disturbing existing entries, a stack proves highly effective because its LIFO principle ensures 1 time complexity for both push and pop operations. Conversely, if you frequently search for items within a collection using keys rather than indexes, then hash tables become essential thanks to their average case constant time lookup capabilities. Memory management considerations. Besides computational efficiency, memory allocation plays a significant role in choosing between various implementations, especially under resource-constrained environments. Dynamic array implementations typically allocate contiguous blocks, resulting in better cache locality, whereas linked list nodes spread out across memory, leading potentially worse spatial locality issues affecting overall speed. This trade-off becomes particularly relevant when dealing with high-performance computing tasks requiring minimal latency between consecutive accesses. Caching strategies optimize cache utilization by preferring sequentially accessed structures over scattered ones whenever possible. Paging systems implement page replacement algorithms considering physical memory constraints dictated by chosen storage mechanisms. Specialized structures for complex problems. Trees offer hierarchical representations useful for representing relationships among entities ranging from file system directories down to abstract syntax trees used in compilers. Binary search trees facilitate ordered traversal, allowing logarithmic time complexity for search/insert/delete operations, assuming balanced configurations are maintained throughout modifications. However, unbalanced BSTs degrade significantly, resembling linear chains, thereby necessitating self-balancing variants like AVL trees or red-black trees. AVL trees maintain balance automatically after every operation, ensuring worst-case log n height guarantee. Red-black trees utilize color properties along with rotation rules to preserve approximate balance, offering slightly relaxed guarantees yet simpler implementation logic. Graph theory applications. Graphs represent connections between objects, making them ideal for modeling networks, including social media platforms, transportation routes, or computer hardware topologies. Two primary graph representations exist: adjacency matrices providing O(1) edge checks, albeit consuming quadratic space relative to number of vertices, versus adjacency lists saving space but needing O(d) time, where d represents degree of node being checked. Depending upon problem specifics, like whether we prioritize checking existence of edges quickly against minimizing total memory footprint, either representation might be preferable. Dijkstra's algorithm leverages priority queue structures, efficiently finding shortest paths in weighted graphs. Kruskal's algorithm benefits from union-find data structures, enabling near-linear time complexity for minimum spanning tree computations. Hash tables and collision resolution techniques. Hash tables map keys onto indices via hashing functions, achieving remarkable speed improvements in lookup operations provided good distribution characteristics hold true. Collisions occur when two separate keys produce same index value, demanding resolution strategies like chaining, wherein overflow buckets store colliding entries alongside original slot. Open addressing methods alternatively probe subsequent locations until empty spot found, although these tend to complicate deletion processes compared to simple chain-based approaches. Separate chaining uses secondary containers, often linked lists, at each bucket position, handling collisions gracefully even under uneven distributions. Probing methods include linear probing, quadratic probing, and double hashing, aiming locate next available location following collision events. Priority queues and heap implementations. A priority queue maintains elements according to specified priorities, ensuring highest priority item gets processed first regardless of insertion order. Heaps implement binary heap structures supporting efficient extraction of maximum/minimum values depending upon whether it's a max heap or min heap configuration respectively. Operations like sift-down/sift-up maintain heap property with amortized logarithmic time complexities suitable for numerous scheduling and optimization problems encountered daily. Max heaps, useful for task prioritization where most urgent jobs must execute before less critical ones. Min heaps, ideal for scenario involving tracking smallest elements dynamically such as median maintenance tasks. Design patterns involving custom data structures. Sometimes standard library offerings don't suffice, requiring custom implementations tailored specifically towards application needs. Implementing tree structures allows faster prefix searches, beneficial for autocomplete features seen commonly today inside search engines and mobile keyboards. Additionally, Bloom filters provide probabilistic membership testing, proving extremely handy in cases where false positives acceptable but false negatives unacceptable. Tree implementation enables word prediction by storing characters hierarchically, reducing search times exponentially compared traditional dictionary lookups. Bloom filters minimize disk I/O costs associated with verifying presence of records prior actual database queries, leveraging set theory principles. Performance benchmarking practices to ensure selected data structures meet required standards. Rigorous benchmarking procedures should accompany implementation stages. Profiling tools help identify bottlenecks, revealing areas needing improvement related either to CPU cycles consumed or memory footprints generated. It's also wise to consider asymptotic behaviors alongside empirical measurements, since theoretical limits sometimes differ substantially from practical outcomes observed in real-world settings. Time complexity analysis helps predict scalability trends, useful estimating behavior under increasing input sizes. Space complexity evaluation reveals potential memory leaks, identifying inefficient allocations contributing unnecessarily to garbage collection overhead. Future trends in data structure design. Rapid advancements continue shaping future directions, influencing what kinds of structures will dominate upcoming years. With rise of big data, analytics emphasis shifts toward distributed processing frameworks utilizing novel partitioned structures, facilitating parallel computation across clusters. Moreover, quantum computing introduces entirely new paradigms, challenging classical assumptions regarding information storage and manipulation possibilities. Distributed hash tables enable decentralized key-value storages, distributing load evenly among network participants, enhancing fault tolerance levels. Quantum data structures explores superposition states, allowing simultaneous exploration of multiple solutions, promising exponential gains theoretically achievable only via quantum mechanics phenomena. Conclusion: mastery over diverse data structures equips developers not merely with technical skills but strategic foresight necessary navigating ever-evolving technological landscape successfully. By thoughtfully evaluating factors impacting selection process, such as expected operations frequency, memory availability, and concurrency demands, you lay solid foundation upon which robust performant programs can flourish.